I'm Dawn Wright, Esri Chief Scientist, and it's my great pleasure to also welcome you to our, I should say, new Esri Ocean Weather and Climate Forum, given that we are in this virtual format. And along with Lorraine, I'd like to thank you for taking time out of your valuable day, especially after such an unusual day yesterday, as we all know, to attend this very important discussion. And I hope it will still be a conversation in terms of the role that ocean, weather, and climate play in the survival of our planet, in the survival of us as humans, and certainly with all of the creatures and habitats, all of the businesses, everything that is our reality on this planet. To this end, we are going to talk a couple of times about a survey that we'd like for you to participate in. So I'm going to quickly just share the information about this before I introduce our first speaker. So we are trying to discern, especially as this is a forum, some of the salient issues, and many of these issues remain with us. They've been with us for many, many decades. And of course, that is around ocean data. So we have developed a survey about ocean data that we have done in conjunction with the Center for the Fourth Industrial Revolution Ocean in Norway. This center is one of our new partners that we're very pleased to work with. And this feedback will actually go to the World Economic Forum and their initiatives, to the United Nations and their initiatives, particularly with the United Nations Decade of Ocean Science for Sustainable Development. And we thought it'd be a wonderful opportunity with over 1,000 of you participating with us to take this survey. Now there is an incentive. So if you go to this link or if you use the scan code there, and if you participate and enter your name and your email address, you will also receive a free download of the new book, GIS for Science, Volume 2, which is about to hit the streets in terms of hardcover, but you will receive a free digital version, and you'll also receive a free digital version of Ocean Solutions, Earth Solutions, the second edition. So I wanted to make sure that you had that opportunity. We'll be putting this information up again throughout today and tomorrow, but I wanted to let you know about that. But now it is my great pleasure to introduce our first plenary speaker. We are very, very excited about Steve Weisberg joining us today. Steve is the Executive Director of the Southern California Coastal Water Research Project, which you will hear about in his remarks. This is a research consortium that was formed by 14 California water quality agencies to ensure a solid scientific foundation for their management activities. So many of you in the audience can relate to this. Each and every one of us depends on a water quality agency in our community. So his research and those of his colleagues focuses on developing molecular tools to support environmental monitoring. And he also serves on the governing board and the scientific advisory committee for several other organizations that are involved with the development and the adoption of new technologies, including the Southern California Coastal Ocean Observing System, or SCCOOS, the California Ocean Protection Council Science Advisory Team, the California Water Quality Monitoring Council, the California Sea Grant Advisory Board, and the Environmental Protection Agency's Board of Scientific Counselors. So Steve does a lot of wonderful work for our scientific community, for our state, and for the nation. And his colleagues are users of GIS. He received his PhD in biology from the University of Delaware and his BGS from the University of Michigan. And he joined the Southern California Coastal Water Research Project, or SCWRP, get used to that wonderful acronym, SCWRP, in 1996. So he's going to talk to us today about the problems that we face with water quality issues, but also the interfaces that are needed in order to solve these problems. So we're very, very excited to welcome Dr. Steve Weisberg. So Steve, over to you.
Wonderful. Thank you for that wonderful introduction, Don. Tremendous honor to be here. I was impressed when I saw the list of people who had been plenary speakers in the past, and I hope I'll keep up with that. The starting point for the talk is that Esri has really produced some amazing GIS tools, a real leader in the field, and really helped transition people into the use of kind of spatial statistics and GIS tools. Initially, these were focused on land-based activities, but Esri has done a wonderful job of pivoting to incorporate a bunch of ocean applications. So what Don has asked me to do is to share what are some of the most important issues to which these tools are being applied, and to kind of look forward a little bit into some of the ways that we see things moving forward in the future for potential other applications. She asked me to reinforce what my organization is and why the GIS tools are so important to us. So as she said, we're a research consortium that's formed by 14 leading water quality management agencies. We don't do policy, we don't do regulation. We are basically a research and development arm for those agencies. And we judge our success not just on things like scientific publications, but whether the science is actually being used by the agencies that we are here to support. We have an incredible privilege, we have an incredible challenge. The privilege is the heads of those 14 agencies serve as our governing board. We get them together once a quarter for 3 hours just to hear what's new in science that should affect the way they manage. A tremendous opportunity for providing interface between science and management. It's also a responsibility, it's also a challenge, because most of the heads of these agencies don't have PhDs in the sciences. A few do actually, but more come from engineering backgrounds or even from legal backgrounds. And so we've got to communicate that science in ways that make it easy for them to obtain the information we're trying to transmit. And spatial statistics are just a very important part of that process. Don mentioned that I would talk to you about some of what are the issues that we work on. You see 4 on the board here. When we tend to think of contamination, the first thing that goes to mind are toxic contaminants. PCBs in the old days, or things like perfluorinated compounds now is probably what you hear about most. Or even things that we're even debating whether they're toxic, like microplastics. Another category is microbial water quality. Is it safe to swim? Is it safe to eat the shellfish? How do we monitor that? How do we determine that? Eutrophication, probably the one that you hear most about, particularly if you live in the Gulf of Mexico. What happens to all those nutrients we put in? And what you hear about is oxygen dead zones, algal blooms, things like harmful algal blooms. These are some of the issues that we focus on. And of course, the biggest one that dovetails very well with the rest of this conference, climate change, of which the 2 biggest on the ocean are probably acidification, as we have CO2 in the atmosphere as it basically bleeds into the ocean. You're changing the ocean chemistry and acidifying the water. And then, of course, sea level rise. Now, I decided not to do the talk giving you examples of what these issues are, but really to talk more from the perspective of kind of how are we using GIS to affect each of these issues. And as I do that, it also dawned, there's your pun, dawned on me that one of the reasons that I was asked to do this is I'm an old guy, and I've been around and I've had a chance to see how GIS has been used over the years and how it has changed in the ways that we use it. So you can see up on the screen 4 ways that I've envisioned an involvement of GIS use. Obviously, it started out with maps, then it moved a little bit more into how do I use multiple layers to conduct data analysis, but we've added dimensionality as we go. So with maps, it was 2D, then it moved to 3D. As we added in models, they went to 3D. And I'm going to talk to you about ultimately what I see the latest expansion, how we enhance the user interaction by things like Shiny apps. So let's get started on that history. This is a map that is probably right now looked at in the most simplest of ways. My God, why do we have Steve do this? He can't even put any kind of stuff that's going on in the landscape. All he's got is a map with a few dots on it. But this is a map that, in my mind, was kind of groundbreaking 30 years ago. This is a map of our regional monitoring program stations in the ocean. My organization, SCCOOS, runs a regional monitoring program where we go out and we try and assess the overall condition of the Southern California bight. Each of these are dots where we take sediment samples for sediment chemistry, sediment toxicity, benthic fauna. We do fish trawls to look at fish tissue contamination. And it's nothing but a bunch of dots on a map. And you'd think, well, that's not very sophisticated. But I want to give you history to talk about how important that was. 30 years ago, where were we? You see the upper left, you see floppy drives. If you had a hard drive in 1990, you had a high-end machine. And if you had a hard drive, it didn't have a 10 terabyte hard drive. It didn't have a 10 gigabyte hard drive. It had a very expensive 10 megabyte hard drive. When we did the internet, again, I probably didn't even get my first email account till the mid 90s, probably 93 or 94. So 30 years ago, a map like this, pretty darn big deal. And of course, when we hooked up to the internet, it wasn't all wired to your house. You did it through the phone lines. But probably the most important one to look at in the graph is this thing on the lower left. I wish we were in person so I could see your faces and see how many people could raise their hand if they knew what these are. But what these are for you youngins is these are press-on letters and numbers. When we used to make maps, if you go back 30 years, if you want to make a map like this, almost every academic department had a graphic artist on their staff because that's the way you made maps. And the graphic artist either did it with pens because they were very good at that, or more frequently what they did is they had these press-on numbers and letters. And so what you do to create a map like this is you'd sit there, you kind of create some map by an artist, and then you sit there with your rub-ons and put the dots on individually. GIS so completely transformed our ability to convey information. Another way that was very important, I mentioned our regional monitoring program. The regional monitoring program is actually a stratified random design. It's got a random component because we want to be able to extrapolate from the locations we sample to all of the other places that we sample. So as a for instance, if you were trying to guess how many people were going to vote which way in an election, as just happened yesterday, you wouldn't just go to your grandmother's bridge club and say who's going to vote for what, because you wouldn't expect that that sample would be representative of the country as a whole. So what you would do is you would try and find a way to sample randomly from the population. In order to do that, you have to be able to define the population and then randomly allocate dots, in a sense, to that. In particular, I also mentioned that we use a stratified random design. The reason is that we want to be able to make estimates not just for all of Southern California, but for a variety of subpopulations. So some of those subpopulations have to do with things like depth. You can see here inner shelf, mid shelf, outer shelf. Or it might have to do with uses like a marina versus a port versus the rest of the MPAs. Or for those of you who know California, we have these areas called marine protected areas that are special protections, and you want to see whether or not the water quality or the sediment quality there is better or worse than it is in the other areas. So you stratify and then you take random samples from each of those. But how do you do that? Well, in order to do that, you've got to have the layers. You've got to have the kind of maps that I have here that allow you to go in and define the population you're sampling from and then allocate samples randomly to that. GIS just changed our ability to do this kind of sampling. Of course, at the back end, you want to be able to put the data out into some sort of format. And again, you go back 30 years, I would send you a Excel file, even maybe it was probably Lotus 123 back then, or a CSV file. Now we draw maps routinely. What's really nice is that we can draw maps that have dots of different colors or dots of different shapes, and then you click on a dot and you get this kind of thing that gives you information about the outcome for that site or allows you to download it. In addition, you can even make complicated dots because this is a toxicity dot. And you can see that we have in here, the dots are actually broken up into multiple toxicity tests. So you can determine whether or not something's non-toxic to everything or whether it's toxic to only a subset of the kind of critters that were tested. Pretty powerful ways to convey information. I focused so far on sediment contamination, but I also want to give you another example of how this is being used to display data. So I mentioned beach water quality is one of the most important things we do in ocean monitoring. People want to know, is it safe to swim? a group called Heal the Bay. They're a environmental advocacy group located in Southern California, has basically assembled all of the data up and down the entire West Coast. They interact with the health departments, the environmental monitoring groups out of the stormwater agencies, the NGOs that monitor, and they put the data out in a GIS format on a real-time, actually it's more like every week basis, and it's put out on a map that looks like this, where the number in there are the number of sample sites in that vicinity. So you have to kind of zoom in. If you zoom in, you get something that looks a little bit more like this. In some cases, you get down to where you've got a single station and you put a happy face or not a happy face. And in some cases, you still have this. If you want to find out more, you click on one of these happy faces or whatever face it is, and you get something that looks like this. So I happen to actually click on one that's a beach that actually has a grade right now of an F for this past week. You get what the grade is, you get who collected the information, so you can find out if you can go talk to them if you want more information. You get multiple pictures of the beach, so not only do you know what the beach looks like in general, but actually even where the specific sample point was. And then you even get the history. So while this beach had an F grade this week, it had a decent history over the last several months of doing A+, and then some other period back here, not so great. I show you this one, not just to talk to you about how we can do this, but how important this is. That Heal the Bay data display has become so popular. It basically reaches out to all of the swimmers. They check it before they go to the beach. That has become one of the key pieces in how we make even management decisions. So for instance, the state of California for many years had something called the Clean Beaches Program. There's a set of bonds that they passed to clean up the beaches. Over $100 million of bond funds went out. And one of the key factors in determining where bond funds go was the Heal the Bay grades for those beaches. Why? Because you want to clean up the beaches that have the most problems the most often. It's also how a lot of the management agencies gauge their success. In addition to that visualization, Heal the Bay actually puts out an annual report card that summarizes that information. It even creates a list of what are called the beach bummers. I'll tell you that one of the reasons this is so successful is, of course, the fact they're being able to pull that data together. Another reason is they actually have developed a grading system, so it provides an interpretational context. But I'll also argue that it's the ready access to the data and the visualization of the data that makes it so popular, that it's used not just by the public who wants to go to the beach, not by the legislature who wants the big picture of how things are doing, but scientists even also go to it to gather and download the data that they need for individual sites. So that's kind of the background on how we use it for map making. I'll tell you that the next bigger thing, though, is when we have multiple layers, how do we use it to conduct spatially explicit data analysis? So I'm going to give you two examples there. This is where we have multiple layers that we pull together. Example number one, wetlands on the edge. The state of California has a bunch of wetlands. Sea level is rising. They have to figure out how they're going to manage. They essentially have three choices. One, they can help the marshes accrete. They can pour sediments on there or do other things that alter flow that allow them to accrete and keep up with sea level rise. Possibility number two is they realize they can't do that, so they'll let the wetlands migrate inland as sea level rises. Doesn't work all the places because in some cases you have some pretty hardened landscapes above that. Or alternatively, resign and determine that some of that is just we don't have either of those options. So this is going to be lost wetlands. It's going to become subtidal habitat. The state of California went through and developed a strategy for what they're going to do, prioritize which wetlands they're going to try and save, which ones they're going to move, which ones they're going to give up on. And it was all done by GIS. You had to have a variety of sea level rise scenarios, kind of mapping where, if you get different levels of sea level rise, that will start to impact the wetlands. You have to know where the wetlands are. You need to know what the species composition are in those wetlands, because some species are more amenable to accretion than others. You also need to know where the upland use patterns are. So again, a good example of where GIS became the mainstay for making this plan for the future. I focused it on wetlands, but here's an example in the San Francisco Bay where they're doing the same thing for wastewater infrastructure. Here's an example in the picture of a wastewater facility. This one happens to be the Hyperion facility in Los Angeles. You can see how close it is to shore. Naturally, that's what it's going to be. You want to treat the water before it's discharged to the ocean, and you want it relatively in the lower part of the watershed. But that also makes it amenable to a sea level rise effect. In San Francisco, they've gone through and figured out where those are and done the same things in a sense that we've done with wetlands for wastewater treatment plants. Second example I want to give you is one that goes back to our regional monitoring program. In addition to what we do on the oceans, we also have a stream monitoring program in the coastal zone. One of the things that we measure is the amount of plastic, the amount of plastic bags, and even other kinds of plastics. What's happened is over time, different municipalities of different sizes have started to adopt different types of bans. In some cases, plastic bag bans, in some cases, styrofoam bags, and they want to know, is this effective? So here's an example where Los Angeles County had actually put in a bag ban. The other surrounding counties had not yet. They have since. In fact, statewide, they have now since. What they wanted to know, what Los Angeles wanted to know, did it make a difference? So again, we're able to take the legislative or regulatory or management background and overlay it onto our monitoring background and subset the data. And here's an example where you can see, this is the area without bans, this is the area with bans, and you can see how much difference occurred in those areas. Again, wonderful use of GIS tools, and it informed, should we move forward with bag bans in other locations? Well, that's a video. Video doesn't want to, oh, here we go. Let's see if we get going. Okay, the next dimension I told you is real time, or I shouldn't even say real time. I should say, in some cases, real time, but modeled output. This adds a dimension of essentially time. This is a very important dimension because as we incorporate models, we want to see what the outcome of models are. We want to see how plumes in this particular case are moving around. And this provides a newer challenge. It also provides a tremendous opportunity to convey information. Here's an example of a model that I've put down into kind of a 2D thing. This is something that Don mentioned, SCCOOS, the Southern California Coastal Ocean Observing System. They've actually developed models that predict harmful algal blooms. Why do we want to do that? Well, if you're a shell fisherman, you want to know, when am I going to have a harmful algal bloom? Because you're not allowed to remove your shellfish. You're not allowed to harvest them after you've had one of these harmful algal blooms, because or if you do remove the shellfish, you have to move them to another location and depurate them before you can sell them. So knowing when that's going to occur and having some advance notice, tremendous opportunity. Another opportunity is mammals, mammal care centers. These kind of algal blooms, particularly one called Pseudonychia that releases a toxin called domoic acid, affects the behavior of things like sea lions. And when you have a big bloom like this, you'll often have sea lions wash up on the beach. So having the mammal rescue centers know when this kind of bloom is likely to occur, having 2 or 3 days advance notice, gives them the opportunity to staff up and get ready. Alternatively, even looking from a history perspective, again, a lot of these models you can work backwards. We don't sample everywhere. We sample at a very small subset of sites. So the models allow us to, in a sense, extrapolate the sampling to a larger region. You want to know, oh, wait a minute, I got a whole bunch of mammals that are washing up on a beach. What caused it? Is it possible that that was an algal bloom? Again, their ability to go back and look at kind of these things, but you have to have the ability to convey this information over time. And that's exactly what's happened. It actually presents an interesting challenge for groups like Esri, because most of these models aren't done within the ARC software. They're typically done in something like MATLAB and an R. So you've got to develop an interoperability that allows you to transition these products. And I've seen some pretty good examples where Esri has done that. Okay, I'm going to finish up by talking about what I call enhanced user interactions. This is where I think we're really at now. What we're finding is, particularly as we do models, but even if we just subset data, people want to be able to interact with the data. They want to be able to look at scenarios and say, what if I made this decision versus I made that decision? How do the models help me with that? This is something that really requires, again, the merger of statistical science and spatial science. And this is an area I'm very glad to see where Esri has developed its R bridge, because a lot of this work is done in R. So let me give you a couple of examples of this. This is one from Tampa Bay. In Tampa Bay, they are trying to figure out what are the critical thresholds that they should be using as they manage. And one of the thresholds they have is light attenuation. The issue there is they have a lot of seagrasses on the bottom. And if they have too much nutrients in the water and they have too much chlorophyll growing in the water, then the seagrasses, which are important habitat, get shaded out, the seagrasses die. So they have to figure out, okay, how do I manage things to keep acceptable light attenuation, and in this case, chlorophyll being the driver that affects the light attenuation. So what they're able to do is create sliders, where the sliders allow the manager to say, what if I move the threshold to this? And they get two outputs on this dashboard. The first is, how would things have changed over history if they had had that threshold at that time? But the other part, of course, is you want to be able to see, where are the problems? Where are the areas that the target is met and not met? And you can see that here we even have the ability to do sliders in 3 or 4 different regions. This is Old Tampa Bay, this is Hillsborough Bay. So again, here versus here. You can change the sliders to affect what are the thresholds you're aiming for in different regions, which are, of course, even run by different counties. Tremendous tool. Here's another example, sea level rise. This is sea level rise in Newport Bay. This is kind of where we're at right now with sea level rise. Here's a tool that has been built to go, okay, I want to see not what it is now, but what's it going to be in the future? And you've got a series of checkboxes of different years, of different percent chances. In other words, you're looking at the 99% worth, or you're looking at the 50% mean. Are you looking at the annual worst, or are you just looking at king tides, which we know are going to be happening? Tremendous opportunity as you're planning, what are my management options? It presents a challenge because the software has to be able to keep up with this, in a sense, infinite dimensionality, as the users can pick any of a series of options. So I'll finish up by saying what's next. I'm telling you that right now, where I see the use of these Shiny apps and other kinds of interactive tools as being what we're really working on now, but I see really where the future is going is integrating even more the monitoring, the modeling, and spatial science. In the ocean world, and I think our next speaker is in the atmospheric world, a lot of what goes on is what's called assimilative modeling. You can't be everywhere at every time in your monitoring, so you use modeling. But on the other hand, there's a lot of information that comes from the monitoring. The monitoring, in a sense, can help you on a continuous basis to improve the model as you're assimilating the real-time monitoring data, whether that's satellite monitoring data or instruments that we put into the ocean that report out in real time. If you can assimilate those into the models, they become that much better. But those are inherently spatially based activities. And of course, even integrating more, the ability to alter the models and do those kind of Shiny apps, I think is really where the action is going to be into the future. That's one man's opinion. I'm actually very excited to hear a lot of what's going on in the rest of the forum and about what you all think are the other things we can do next. And with that, Don, I don't know if we have time for questions, but I'm glad to take them if we are.
Yes, we do, Steve. That was absolutely fantastic. And throughout the question and answer, one of the things that you've gotten the most questions about is your actual slideshow presentation, whether or not you will be able to share that maybe as a PDF. I have been answering those questions throughout your presentation to remind everyone that we are recording these, and the recordings will be available. But in the meantime, I've given people the liberty to take screenshots of what you have showed as well. But are you willing to share not only your slides, but you had so many wonderful links in your presentation?
I'm glad to do it. I'll shoot you a PDF over, Don, as soon as we're done here.
Okay, great. So for all of you in the audience, we will try to share that PDF with all of you as soon as we can. One of the things that I loved was your focus on history, moving from the older days of GIS to the present. And I think the audience enjoyed that as well. And we have one question here about assimilative modeling. Would you consider that to be another term for developing and using a digital twin of the environment?
I've not heard the expression digital twin before, so I don't feel I can give you a good answer to that.
Well, I think I would say that yes, your assimilative modeling is on the way to that, because a digital twin, as we're using it now in the GIS world, is essentially creating an actual digital simulation of the environment, and that simulation allows us to predict and to plan. And particularly with regard to infrastructure, you had some wonderful examples of, for instance, the wastewater infrastructure along the coast, and ports, because our teams at Esri work quite a bit with ports as well. And so there is the idea now that we can create a digital twin in terms of the buildings, the pipelines, the roadways, and then we can model and plan based on that on the human side, but now on the ocean side as well. So great. I will, we have time for one more question, and maybe two. The first one here is, could you speak to the importance of elevation data to the analysis that you were speaking of?
Absolutely critical. Obviously, we're talking about sea level rise. We're talking about, in the short term, things that are on the millimeter kind of level. So having good elevation data is critically important. I think the thing that works to our advantage is we've got a pretty good handle on that. I think there are groups like NOAA that do LiDAR surveys and just produce great elevation information.
Great. And we do have time for one final question. Have you or the folks at SCCOORP used story maps to convey your water quality data, and also how to interpret that water quality data to the public or to the agencies that you serve?
Intriguingly, Dawn, if you'd given me 3 more minutes to talk, I would have included a few slides about story maps, because I think they are a very important part of the process. And it is, in a sense, one of the advances that has happened. It's the ability to not just see the data, but to really get an understanding of the context of the data. And some of that context I showed in the Heal the Bay stuff, which showed maps, but also showed pictures of the site. And if you click on more of those, you'd see even more pictures of the site, even more descriptors of the site. But story maps just take it one step further. So yes, very important part.
Oh, terrific. Well, perhaps you could throw a couple of those in when you prepare your PDF for people to download later. Okay, well, thank you so much, Steve. We're going to have to let Steve go because he's got a meeting that he has to get to very quickly, and we're so very glad that he was able to make the time in his schedule to give this plenary to us. So thank you again to Steve.